Section 1.5 is solving inequalities. I can solve and graph inequalities. Big ideas for this section. Just as properties of equality can be used to solve equations, properties of inequality can be used to solve inequalities. Properties of numbers and inequalities can be used to solve an inequality by finding increasingly simpler inequalities that have the same solution as the original. Take note on page 33, shows less than, greater than or equal to, or less than or equal to 4. So in the graphs on the chart, 4 is a boundary point because it separates the graph of the inequality and the rest of the number line. So the x less thans go to the left, x greater thans go to the right. If there's an open dot at 4, it means that 4 is not a solution. A closed or filled in dot means that 4 is a solution. In example 1, we're going to write an inequality from a sentence. What inequality represents a sentence 5 fewer than a number is at least 12? Well, 5 fewer than a number, we want exactly 5 less than. So we're going to take a number minus 5. Now, it can be at least 12. So could it be equal to 12? Yeah. Could it be more than or less than? If you're not sure, check a number. Could it be 20? Is 20 at least 12? Yeah. Could it be 5? 5 is not at least 12, so it's got to be greater than or equal to 12. In order for it to be at least 12, that means 12 is the smallest it could be, and the number that we want has to be greater than or equal to. Now, what inequality represents a sentence? The quotient of a number and 3 is no more than 15. Okay, quotient means division of a number and 3 is no more than 15. Could it be equal to 15? Yep. Could it be greater than or less than? Again, if you're not sure, try some numbers. Could it be 20? No. 20 is more than 15. That can't work. Could it be 10? Yeah, 10 is no more than 15, so it could be less than or equal to 15, but it can't be greater than. Okay, so no more than means less than or equal to. Just like with equations, the solutions of inequalities are the values that make the statement true. The properties of inequality we use are similar to the properties of equality we use to solve equations. There's just one major difference. Anytime we multiply or divide each side of an inequality by a negative number, we have to flip the inequality symbol. So when we add and subtract, it's the same, but if we multiply or divide by a negative, we have to flip the inequality. So take note, properties of inequality on page 34 talks about our transitive property. If A is less than B and B is less than C, then A has to be less than C. It talks about our addition and subtraction properties. We can add or subtract the same number on both sides and get equivalent inequalities. And our multiplication and division properties, which say if we multiply or divide the same number on both sides, our inequalities are equivalent as long as it's positive. If we're dividing or multiplying by a negative, we have to flip that inequality in order to keep them equivalent. Example 2 here, we're going to solve and graph this inequality. So the first thing I'm going to do is get rid of my parentheses and distribute. Negative 6x plus 15. Then I'm going to bring down the rest of my inequality. Plus 1 greater than or equal to 4. Combine our like terms. Again, when we go about solving an inequality, it's the same steps that we go about solving an equation unless we multiply or divide by a negative. So here, I subtract 16. And now, because right here, I have a negative 6 that I'm going to divide by, when I do that, I've got to flip my inequality. So I'm going to get x, instead of being greater than, now it's less than or equal to 2. And we have to do that in order to keep it equivalent. If we plug numbers in to check there, guys, that's what we'd have to do to keep it equivalent. Now, to graph it, remember on our number line, I want our boundary point. I want one number on each side. and I want where 0 is. And it doesn't have to be by scale, so if it was like 15, we wouldn't have to count all the way down to 0, but just show me that 0 would be on the left side. We put a circle at our boundary point, which here is 2. Because it's equal to, I'm going to fill it in. It's like we filled in that inequality by adding the equal. And now I'm going to pick, we want numbers less than or equal to 2. So numbers like 1, for example, not 3. So we're going to shade the side that has our test point in it, 1. Otherwise, if our variable is listed first, we can have our inequality match our arrow. But it's always a good idea to use these test points on either side to see if it's true or false. Go on the side that makes it true. Feel free to pause here and give this a try if you'd like. I'm going to distribute first. Bring down the rest of my inequality. Combine my like terms. Add or subtract. Then, because I'm dividing by a negative, we have to flip our inequality. So it's going to be x is actually less than or equal to -8. On my number line, we want our boundary point, 1 number on each side, the consecutive number on each side, and 0. I put a circle at my boundary point. Here, because it's equal to, I'm going to fill it in. And we want numbers that are less than -8, so numbers like -9, for example. We're going to shade on the side that our boundary or that our test point works on. Or again, because my variable is listed first, I can match my inequality with my arrow. In problem 3, a movie rental company offers 2 subscription plans. You can pay $36 a month and rent as many movies as desired, or you can pay $15 a month and pay $1.50 to rent each movie. How many movies must you rent in a month for the first plan to cost less than the second plan? So first of all, figure out what we're trying to figure out here. We're trying to figure out for our first plan to be less than our second plan. Then figure out your costs. So with our first plan, it says we can pay $36 a month and rent as many movies as we want. So my total costs there are $36. With my second plan, it says we have to pay $15 a month and we pay $1.50 each movie. So $1.50 times the number of movies. Now we solve. I'm going to subtract 15 to get my variable alone on one side. And divide by 1.5. I'm going to get 14 is less than m. So, we have to watch more than or rent more than 14 movies in order for this to work. In order for the first plan to cost less than the second plan, we have to watch more than 14 movies. If we watched exactly 14, they'd cost exactly the same, and that's not what we're looking for. But it could be anything more than 14. We could watch 100 movies and it'd be better. So it's got to be more than 14 or write it as an inequality. We could have left it like this. But again, it's not just 14. 14 tells us how many it would be even. It can be anything more than that. Now, a digital music service offers 2 subscription plans. The first has a $9 membership fee and charges $1 per download. The second has a $25 membership fee and charges 50 cents per download. How many songs must be downloaded for the second plan to cost less than the first plan? So here, we want the second plan to cost less than the first plan. So my costs here for the first plan is a $9 fee and $1 per download. So $9 fee and 1 times the number of downloads. The second has a $25 fee and charges 50 cents per download. Now, we're going to go ahead and solve. I'm going to get my variables together on one side. Number parts together on the other. And then I can divide. And again, if we multiply or divide by a negative number or by a positive number, we keep our inequality. It's only if we multiply or divide by a negative that we have to worry about it. So 32 is less than the number of downloads, so we could say more than 32 downloads. But again, it's not exactly 32. Exactly 32 would tell us when we break even. We want to know when it would be second less than first. So we'd have to download more than 32 songs. Here we're checking for no solution or all real numbers. Is the inequality always, sometimes, or never true? It's going to be always true if our inequality at the end is true every time. So no variables left, and it gives us a true statement. Sometimes true if we have a variable left, x less than 4, x greater than 5, things like that. And never true if the inequality that we get is false. So something like 4 is greater than 10. Okay, that's false, so it's never true. Distribute first. Get our variables together on one side. Here, -6 plus 6 is 0 on both of them. So I'm left with -2 is greater than 7, which is not true. So since -2 is not greater than 7, this is never going to be true. Here I'm going to distribute. Combine like terms. Get my number parts together. Or sorry, my variable parts together. On one side. 3x minus 3x is 0. So I have -15 is less than or equal to 8, which is true. So this is always going to be true. Here I'm going to distribute. Okay, get my variables together on one side. 8 minus 8, 0 in both spots. I have -12 less than 8, which is true. So this will always be true. Again, always true if our statement is true at the end. Never true if our statement is false at the end. And sometimes true if there's some values we could plug in for our variable, because our variable is still there, that would make it true, and some that we could plug in that would make it false. And I will continue on in another video.